This part of the course is for people who have already done a course on finite element techniques, at least linear finite element techniques. If you have not done a course on finite element techniques, don't worry too much. I think you will get the idea of what I'm trying to tell you in this lecture. And then when you get to do a finite element course, please try to fill in the details. Okay, so we are going to see how you can calculate the stress intensity factor in a finite element mesh, linear elastic finite element. And especially I'm going to concentrate on the isoparametric element formulation, which you might have learned in your finite element course. In the isoparametric formulation, your uh, position at any position inside the element x is um, in the 2D case, it is approximated in terms of shape functions, which are functions of zeta eta for the 2D case, where zeta eta are the parent coordinates of the element. Similarly, it's called isoparametric because when you approximate the displacements, you use exactly the same set of shape functions and write the displacement at any point inside the element in terms of the shape functions times the nodal displacements that you have calculated from FEM. So the position is interpolated from the nodal positions in the same way as the displacement is interpolated from the nodal displacements, and that's why this element is called isoparametric. But we will start with the 1D isoparametric element whose parent is of this type. So this is the parent element where zeta is the only parent coordinate, and it goes from, and it has nodes at -1, zeta equal to -1, zeta equal to 1, and zeta equal to 0. So this element is mapped into a physical element. Let's say it's mapped into a physical element at the tip of a crack. So this is your crack, and it is mapped into a physical element where nodes 1 and 2 are the end nodes, and node 3 does not lie exactly at the center but is shifted slightly towards node 1. Okay, so if the length of the element is L, the position of node 3 is at chi times L, and chi is a parameter that is as yet undetermined. We are going to determine it through what we are going to do right now. Now, if you look at this isoparametric 1D element, the displacement at any point inside the element is at any point zeta, any point marked by parent coordinates zeta. Let's say here, this point maps to, let's say, this point here. So the displacement at this point is expressed in terms of zeta, and that is done with respect to these shape functions which I call ni zeta, and there are as many shape functions as there are nodes. So in this case there are three shape functions as there are three nodes, and each shape function is a quadratic function because shape functions have this delta property, Kronecker delta property, and the shape functions for this case would have to be quadratic since there are three nodes. Now, what are the shape functions? N1 is zeta times zeta minus 1. So you can figure out that when zeta is equal to -1, this is going to be equal to 1, and when zeta is equal to 0 or +1, this is going to be 0. Same for this and same for this. So all of these shape functions satisfy the Kronecker delta property that shape functions should satisfy, and these are the nodal displacement values. These are u1, u2, u3 are the nodal displacement values at nodes 1, 2, and 3 respectively. So With this interpolation, we can now write it as, we can just shuffle the terms around and we can write it as a polynomial in zeta. These quantities, remember, these quantities are nodal quantities, so they are obtained from the solution. So we can write it in terms of a quadratic function, in quadratic polynomial, in terms of zeta. The point to note here is that if I take strains, if I'll have to take derivatives with respect to u, derivatives of u with respect to x, or whatever this coordinate, this direction is. So when I take the derivative, I would get a linear function in zeta. So the stresses will also contain those linear terms. The point to note here is that the stresses do not necessarily contain the 1 by square root x terms, 1 by square root x terms that are needed in order to approximate the state of stress that prevails here. We know that the state of stress that prevails here would go as 1 by root r, which along this direction would go as 1 by root x. But this approximation in general, is not going to have that 1 by square root x variation if you use it just like this. It is going to be always going to be a linear function zeta and a linear function in x. Okay, so what we are going to show is that if you choose this chi factor appropriately, in other words, if you move this mid node 3 towards node 1 by an appropriate amount, then you can have the 1 by square root r singularity reproduced in these in this approximation. So we are trying to find the actual value of chi that would allow me to reproduce the 1 by square root x singularity that I expect in the stresses and strains. So since it's an isoparametric element and the displacements at any point zeta, say this point, is a quadratic function of zeta, the position of this point, so if you are at this point, you have a value of zeta, and this point maps to this point in the isoparametric formulation. So the r of this point, position vector of this point, we are calling this r. So the position vector of this point, magnitude of the position vector of this point, would also be given by the same approximation, because in the isoparametric formulation, the position and the displacement are subjected to the same interpolation functions. So this exact quadratic polynomial would be valid for position as well. So this would be the position r of, we can call it r of zeta of any point that is mapped from zeta. So this point is, if this point is mapped from zeta, it's mapped, this one would be r of zeta, and that would depend exactly in the same way as u does. So this would be r of zeta, and now we can use the coordinates, actual coordinates here. R1 is 0, R2 is L, and R3 is chi times L. So I plug that in, and then r of zeta comes out to be this. I've just put in the values of R1 is 0, R2 is L, and R3 is chi times L. When I plug that in, this is the r that I get. That means given a zeta, this would be the position vector of a crack tip isoparametric element containing 3 nodes, linear isoparametric element containing 3 nodes. Okay, not linear, one-dimensional isoparametric element, quadratic, containing 3 nodes. Okay, so now in isoparametric formulation, node 3 is generally placed at the midpoint. That means zeta is equal, chi is equal to half. If chi is equal to half, then this term becomes 0, and you can solve for zeta in terms of the position as this. This becomes the solution of zeta in terms of r. So what we have is if I'm given the r of this point, I can use this expression. I can use this expression to solve for the zeta where it comes from. In the parent, I can figure out the zeta where it comes from if I know the r and chi is equal to half. Okay. Now, if chi is not half, this term doesn't go to 0. So let's say chi is equal to 1/4. Let's say chi is equal to 1/4, in which case the quadratic term remains, and this term doesn't go to 0. So it's a quadratic equation which you need to solve, but you can solve it and you can show that r is equal to L by 4 1 plus zeta whole square in case r equal to chi is equal to 1/4. And if you solve this, you get zeta to be 2 root r by L minus 1 in this case. When chi is equal to 1/4, r zeta becomes 2 root r by L minus 1. So this is zeta. Given any r in front of the crack tip, any physical r in front of the crack tip, the zeta where it comes from will now depend on this equation when chi is equal to 1/4. Okay. Okay. Now let us put it back. For chi equal to 1/4, let us put it back in this equation. And try to see what u is as a function of r. So I'm going to replace zeta here by r that I have found for chi equal to 1/4, and I'm trying to find u as a function of r rather than u as a function of zeta. So let us see what kind of function u is, what kind of a function the displacement at the tip of a crack is for this particular choice of chi equal to 1/4. If we do that, this is what we get. We see that ur is now a function of root r by L as well as r by L. So the choice of chi equal to 1/4 gives you a displacement that varies as root r by L and r by L, which means that your strains, which is del u del r, now vary as 1 by root LR and 1 by L. Okay, so as you can see that we have now got this root r variation in u, we have got the root r variation in displacement, and this 1 by root r variation in strains and therefore in stresses for an element where the mid side node is put at 1/4 location. So for chi equal to 1/4, this is the strain and displacement that we get, which contain the terms that are also present in the crack tip fields that we have learned from Williams solution. So so the displacement also has this term, and the strain has this additional term. Okay, but we can hope by using this element to be exactly able to reproduce the strain and displacement variations at the crack tip, because the terms necessary for the exact reproduction are already there in the interpolation. Okay, so just to summarize what we have done, uh, we have uh, we have written the interpolation in terms of the parent coordinates. Then we tried for a particular value of chi, we try to replace the parent coordinates by the physical coordinates and write u as a function of the physical coordinates. Once we did that, we took the strain, and then we saw that for a certain choice, for a particular choice of chi, we actually have the correct terms necessary to approximate the Williams displacement and stress solutions if we choose chi equal to 1/4. That's what we have shown here. Now, this is for a 1D case, and let us see how it is for a two-dimensional element. So let's take a quadratic rectangle. So this is a quadratic rectangle, and the numbering is numbering that I have used is like this. 1 is here, 2, 3, 4, and then the mid-side nodes go as 5, 6, 7, 8. If you change the numbering, the story will change. So the shape functions will change from what I'm going to write here if you change the numbering. So the shape functions won't change, the order of the shape functions will change. So now this is your parent, and this is in the zeta 1, zeta 2 coordinate system. And this is the physical element that I'm going to put at the crack tip. So if this is the crack, this is the physical element that I'm going to put, where the nodes 4, 8, and 1 are all collapsed at the tip of the sharp crack. So this is the element called a collapsed quarter point element that I'm going to use, and taking my Q from the 1D case, I would move these nodes 7 and 5 to, so they should ordinarily be at the mid side, but I'll move them to a 1/4 position. Well, not a, I haven't proved that it's 1/4, but to a position defined by chi times L, where chi is not equal to half. Okay, so this is called a collapsed quadrilateral, and then this is the r vector, and this is your theta, and we know how the stresses are supposed to vary with r and theta. We know that they are going to vary as 1 by root r times some function, some angular function of theta. This is how the stresses are going to vary. So we need to have this kind of a term, this kind of a variation inbuilt into our approximation, so that we can approximate the stress fields accurately. If you don't have this kind of a term, stress fields will not be accurately approximated. We would need to have very, very small elements in order to approximate the stress fields. So what we are going to show is that if you used such a collapsed quadrilateral under certain circumstances, you will be able to reproduce this 1 by square root r term in your stresses. So let's see how that goes. So if you take this parent, these are the shape functions. Okay, so shape functions I've given in two sets, where for 1, 2, 3, and 4, which are the corner nodes, these are the shape functions, and for the mid-side nodes, these are the shape functions. For zeta 1 equal to 0, which is zeta 1 equal to 0 is this line. For these nodes, that means for 5 and 1, no, 5 and 5 and I can't read it. 5 and 7, yeah, for 5 and 7, it is these are the shape functions, and for 6 and 8, these are the shape functions. So this is all textbook material, so you can look up any textbook on finite elements, second order isoparametric rectangles, and you will see that these are the shape functions. You can see, you can make out that for this biquadratic element, the shape functions all satisfy the Kronecker delta property, which means that they are one at the node at which they belong. So n1 is 1 at node 1 and 0 at all other nodes. N6 is 1 at node 6 and 0 at all other nodes. So that kind of a property is satisfied, and that's how these interpolation functions are designed. So just accept that these are the interpolation functions, and now we will try to do pretty much the same thing that we did for the 1D element. So in the physical element, now the nodes 1, 4, 8 have all been collapsed. So if you take a crack tip coordinate now, your crack, remember, is here, it's a sharp crack. So if you take a crack tip coordinate, then 1, 4, 8 have 0, 0 as their coordinates, physical coordinates. Node 2 has L minus H, node 3 has LH, and node 5, which is now no longer in the mid side, has chi L minus chi H, and this has chi L chi H, and node 6 has L0. These are the physical nodes, physical coordinates of the nodes for this collapsed quadrilateral. And now we will put these physical coordinates and try to find out R. R, remember, is equal to root over x1 square plus x2 square. So we'll try to find out R as a function of x1 and x2. So the coordinates would be coordinates of any point, say this point, this is x1, this is x2. So for this point, these coordinates x1, x2 would be interpolated in the same way with the same shape functions as the displacements, because the element is isotropic. These are the physical coordinates. So what we will do is x1 is summation of n zeta 1, zeta 2, x I 1. So I goes from 1 to 8, and x2 would be ni So these xi2 and xi1 are the nodal coordinates, physical nodal coordinates. These ni are functions that are given here. These are the interpolation functions given here, and this is how we are going to interpolate the physical coordinates of this point, given that we know these quantities from the definition of the physical collapsed quadrilateral element. So provided that we know these nodal coordinates, physical coordinates, we can find from the interpolation functions the interpolation for this this coordinate x1, x2. So that's what we have done. We have plugged in the physical coordinates and got x1, x2 here. And if r is the distance of the point from the vertex, so I have calculated r. I have calculated r as root over x1 square plus x2 square, and this is what I end up with. This is what I end up with. Okay, so this is a function of xi1, zeta 1 and zeta 2. R is a function of zeta 1 and zeta 2 now, and for chi equal to 1/4, this becomes somewhat simple. So this term cancels out. This term goes to 0 for 1/4, and R is given now by this quantity because the last term has got cancelled, and therefore 1 plus zeta 1 is root R divided by So this is zeta 1 and zeta 2 in terms of r, or in terms of x1 and x2. R is a function of x1 and x2. So this is pretty much what we had done in case of the um, linear one-dimensional element, one-dimensional quadratic element. We had figured out what zeta should be given r. So we had figured out the inverse relation for chi equal to 1/4. In this case, there was only one parent coordinate zeta. In case of the quadrilateral, there are two parent coordinates zeta 1 and zeta 2, and we have figured out a relationship between zeta 1, zeta 2, and r. That's this. This is pretty much the same as the 1D quadratic element. Now, so we can also find the x1 and x2. Here we have found r, so we can find x1 and x2. We simplify this for the choice chi equal to 1/4. So this goes to 0, this goes to 0. And for chi equal to 1/4, this becomes 1/2, this becomes 1/2 as well. Having done that, this is what the coordinate of any point will become. So this is what we need. So we now have the interpolation between zeta 1, zeta 2. Given as zeta 1, zeta 2, I can tell you the point that it maps to, that the parent maps to inside in the physical space, and we also know how r maps to, given a zeta 1, zeta 2 in the in the parent coordinate. Now, the Jacobian matrix can be calculated. So for those who know how isoparametric mapping is done, you would know that there's a Jacobian matrix and the determinant of the Jacobian matrix that needs to be calculated. The Jacobian matrix is simply this, del x1 del zeta 1, but now we have x1 and x2 for this collapsed element in terms of zeta 1 and zeta 2. So these we can calculate very easily. And this is your Jacobian. This is your Jacobian, and now we can plug in. We have expressions for 1 plus zeta 1 from here. We have expression for 1 plus zeta 1 here, and we can plug in these 1 plus zeta 1 values in terms of zeta 2 and root r, and we will see that there would be zeta 2 in these functions, because 1 plus zeta 1 contains root r in the numerator, and there is zeta 2 square to the power 1/4 in the denominator. So it will contain zeta 2, but all these terms would vary as root r divided by some function. So they would all go as root r. So root r would be included in the Jacobian itself. So this is going to be the, this has square, so this will have r. This will go as r. This is square here. So these will go as root r, and this will go as r. So this will be the form of the Jacobian. Obviously, there would be some zeta 2 terms, but root r is included in the Jacobian. So the determinant of the Jacobian will also contain zeta 2, but the determinant would vary as product of these two, that is r to the power 3 by 2. The determinant of j would go as r to the power 3 by 2. Now with this, let us see how the strains are approximated to. So to see how the strains are approximated, we first need to see how the displacements are approximated, and then the strains are calculated in terms of the physical strains are calculated in terms of the inverse of the Jacobian. So if you invert this Jacobian, again you have the root r terms, and the inverse would go like this. Okay, so this is r to the power 3 by 2. J22 goes as r. This goes as root r. This goes as root r. So J inverse would go as 1 by root r, 1 by r, and 1 by r again. So that's how it would be. So the Jacobian contains both 1 by root r and 1 by r. Okay. Now comes the components of strain. So the first component of strain epsilon 1 is del u1 del x1. So that if you know isoparametric formulation, you would know that it is given by J11 inverse. That's this term, J21 inverse, and these derivatives which are calculated in the parent coordinate system. So these are derivatives of the shape function. These require you to calculate the derivatives of the shape functions. So if you calculate the strains in this way, then you can see that I can plug in J11 inverse, for example, I know goes as 1 by r. J12 inverse I know goes as 1 by root r. So if I do this, and there are the shape function terms here, the shape function terms are hidden here. So the shape function terms also have some r variation, and they are also dependent on the nodal values of the displacements. If I do that, then I can split up every strain into three terms, the first depending on 1 by r, the second depending on 1 by root r, and the third being a constant. So the stresses would also contain these terms. So now I have a situation where 1 by r is included in my strains, 1 by root r is also included in my strains. 1 by root r is what I want. 1 by r is a term that that is kind of extra in this story. So and if you look at these b naughts and d naughts, they are all combinations of the nodal displacement. So these terms would carry the nodal displacements. Remember, u1 is so u1 is this. Ni are functions of zeta 1 and zeta 2. So when you take derivatives of this, you would get this times, when you take the first derivative, times ui1. So these are the nodal displacements. They would be hidden in these terms. I have plugged them all together, and they give rise to these constants b naught, e1, d naught, etc. So the long and short of the story is that now you have a 1 by r variation and 1 by root r variation, and these things are dependent on the nodal values of the displacements. Now there is one more trick that I can do. What I can do is I can kinematically couple the nodes 1, 4 and 8. So I can actually make sure that 1, 4 and 8 remain together even after deformation. That means I force the displacements, the nodal displacements of 1, 4 and 8 to be the same throughout the deformation. If I do that, I'm not showing it explicitly here, but you can, it's just a bit tedious to show. You have to actually get these constants and show it. But if you make sure that ui1, ui4 and ui8 always remain equal to each other during the deformation, then you can show that b naught and d naught tend to go to 0. B naught and d naught go to 0, which means that this term, and this term are 0 in the strain and therefore in the stress. So the strain and the stress now contain only terms containing 1 by root r and constants. So the 1 by root r term is there and the 1 by r term is not there when you kinematically couple the collapsed nodes. Okay, so then that is exactly what we need to approximate the Williams solution. So now your strains are designed by this choice of chi equal to 1/4. Your strains are now designed to replicate the 1 by square root r singularity that you expect from the Williams solution in the stresses and strains. So, uh, so we have generated these elements. Now, how do we calculate the stress intensity factor from here? That is also very easy. So let us say we have an arrangement of elements like this. Each of these are elements, and I'm specifically concerned with this element and this element. These elements are all collapsed quadrilaterals with the nodal displacements tied so that they remain the same during the deformation. So we are concerned with with nodes C, B, and A, and C prime, B prime, and A prime, which lie on the upper face and the lower face of the crack. So we are interested in these coordinates. A and A prime are the same, so both are at r equal to 0, both are at exactly the crack tip. So if you now look at the displacements of this, so this CBA, this is a 1D element. This is like your 1D, where B is again at the quarter point. B is again at chi. If this length is L, then this length is L by 4, and then we already have the displacements for that 1D case. We had derived it earlier. So this is the uh, so this is the displacement for the 1D case. Remember, we have got rid of the R by L term. We don't have the R term anymore in the, so we will be only left with this one and this term. So let us concentrate on the root R by L term. So this will be the displacement interpolation in terms of the nodal coordinates in case of the collapsed quadrilateral with the nodes at the tip constrained to move together. So you can also find the displacement from interpolations like this. So interpolations like this would also give you the displacements. You have to express zeta 1 and zeta 2 in terms of r, and then you'll get the displacements. So these would be the displacements for the top element. So the element on the top, displacements along CBA. Remember, the shape functions on these edges and these edges would all be 0 at these three nodes. So they don't appear in this expression. This is UR at any point. So UR can be U1 or U2. The interpolating function would be the same. And this is UR in terms of R, because we have replaced now zeta 1 and zeta 2 in terms of R. So U1 would contain a root R by L term. So this is your U1. And now if you have got U1, we have an expression from the Williams solution for the crack tip opening. So if this is your X1 and this is your X2, we know that the crack tip opening delta is you have U1 given as K1 root R, I think root 2 pi R divided by 4 mu pi, I think, U1 hat theta, and U2 given by a similar expression. So you take U2, so you can calculate the delta 1 in mode 1, you can calculate delta 1 as U2 at R pi. So this is pi and this is R where you want to calculate delta. So R pi and minus U2 R minus pi. So minus pi is here. And at the same location, if you calculate U2, which is upwards here and downwards here, if you take the difference between them, you get the opening delta, crack tip opening delta. And in terms of K1, that should turn out to be this in if you believe the Williams solution. This would be valid very close to the crack tip, so you have this R tends to 0. So if you take this, you have to remember that E prime turns out to be E by 1 minus nu square in plane strain and is equal to E in plane stress. So with this, we have replaced in the formulas that are given in the notes. We have replaced mu from by E divided by 2 into 1 plus nu. If we make that replacement and use for plane strain, we use kappa equal to 3 minus 4 nu, and for plane stress we use whatever expression is there. We will get this. We'll get this easily. There was a problem in the first quiz where you had to show this as well. So this is the expression that we now use to find out what is K1. So take K1 to the other side. So if you want to find K1, what you would do is you would take this limit. And in this limit, this delta 1 FEM is the delta 1 that you find from your FEM solution. This is for mode 1. So if you want to do pure mode 1, then you would find this delta 1 FEM from the solution. How would you find it? You would find it by taking U2 FEM at R pi and U2 FEM at R minus pi. I'm sorry, so error here. So once you do this, you can see that U2 is dependent on root R. U2 is dependent on root R, which means that will cancel with this root R, and you would get a limit of this. The limit of this will exist. If you want to do it for mode 2, then you will calculate delta 2, which is now U1 R pi minus U1 R minus pi, and it will similarly lead to an expression for K2, and you can find K1 and K2 together by taking the difference. So U1 R pi at any R and U1 R minus pi at any R can be calculated from this interpolation. So U at any R is this. It's given in terms of the nodal coordinates, out of which UA is equal to 0. To get UR pi, you take at the nodes C and B. To get at UR minus pi, you take at node C prime and B prime. UA is the crack tip node, so this is always 0. So if you do that, then this is what you will get for both mode 1 and mode 2. For mode 1, you have to use U2. For mode 2, you will have to use U1. So once you do that, you can plug it into this or in the K1 equation to get your stress intensity factor. So these kinds of elements with collapsed quadrilateral elements, second order quadratic quadrilateral elements, are available in most commercial softwares. And in 2D, you can use them to find the stress intensity factor using quite a coarse mesh. You have to mesh the crack tip in this fan-like fashion, and most softwares again have automatic measures that can allow you to mesh like this. So if you use this quarter point elements, second order quadrilaterals, you would be able to derive K1 and K2 both. There is a way of deriving K3 as well, but I'm not going into that. This is just to give you an idea about how stress intensity factor can be derived using finite elements. We will look at other methods of deriving stress intensity factors, other more this is kind of direct. You try to induce the 1 by square root R singularity into your stress approximations, finite element stress approximation, because you know that the Williams solution demands that 1 by square root R exists in the stresses. So this is a more direct method of calculating K1. We will look at more in other indirect methods as we progress in this course. So I'll stop here. In the next lecture we will do a few problems using the stress intensity factor and the fracture toughness.